So hello everyone, we are in the second video. This is continuation on how to design a horizontal screw conveyor step 3 and 4. Step 3 is compute the horsepower requirements if HP, MHP, CMHP, and TSHP. So based on the design data, so we can compute, and also those computed data that we get from the previous video on the step 1 to step 3 on how to design horizontal screw conveyor. So moving on, step 3.1, compute the friction horsepower, which is the FHP. So friction horsepower equals dF times BF times L times S divide 1 million. So the resulting unit is horsepower. So are the required DF, BF, L, and S? So DF is the diameter factor. So selected from the diameter factor chart, page 48 of the engineering handbook. So since we have already the diameter of the screw conveyor, so we can get the diameter factor of 5. So for the BF is the bearing factor, so still selected on the bearing factor chart, page 48 of engineering handbook. So for this design, we got the bearing factor of 1. As we consider, the bearing to be used in this design is component series C1 to C2. So based on the bearing class C2 or C1, so it can be feasible. So we'll consider a ball roller type of bearing. So the bearing factor is 1, as you can see on the table. So for the L, which is given, is 16 feet, and that is the screw conveyor length. So S is the actual conveyor speed, which was already computed in the previous video from step 1 and step 2. So which is 73.64 RPM. So for the FHP, which is the friction horsepower, so we got on the formula, so we got 55 for the diameter factor times 1 for the refactor times 16 feet for the length, and the S is the actual conveyor speed, 73.64 RPM. So divide 1 million, so the resulting horsepower is 0.65 horsepower, the friction horsepower. Step 3.2 is compute the material horsepower, MHP. So material horsepower equals CP times MF times L divide 1 million. So the resulting unit is horsepower, of course. So CP is the capacity material flow rate. So that is given already as part of the design data, is 47,500 pounds per hour. So MF is material factor, which is given also, as you can remember in the bulk material table. So since the bulk density is 50, so within the range of the standard in the table of 40 to 50, 60 pounds cube per cubic foot. So the resulting material factor is 0.8. So L is the length of screw conveyor, which is 16 feet. So the material horsepower equals 47,500 pounds per hour times 0.8, which is the material factor times 16 feet divided 1 million. The resulting is 0.61 horsepower. Step 3.3. So compute the corrected materials power, CMHP. So why is it that we compute the corrected materials power? It is to overcome an upset condition such as minor choke in the inlet or a large slump being conveyed. So it is needed to compute the material horsepower in order to compensate the overloading. It is used to increase the total shaft horsepower of a screw conveyor when the calculated material horsepower is less than 5 horsepower. So of course, the increasing the THP allows the screw conveyor to overcome most upset conditions, reducing downtime and loss of production. So unsa may what are the upset conditions? So overloading. So the correct materials power is sometimes called as the overload factor. So based on the chart, since we have given already the computed materials horsepower of 0.61, so to compensate, we will plot this on the chart. So as you can see on the chart, so 0.61, you raise upward, intersect on the line, curve line, and then go to the x-axis. So you get the corrected horsepower of 1.5 horsepower. So as you can see on the chart, using the materials power, the computed one, and from the x-axis, you intersect through the curve, then going to the left on the y-axis. So you get the 1.5 horsepower, as you can see on the chart. Step 3.4, compute the total shaft horsepower or THP. So total shaft horsepower is equals to FHP plus CMHP divide E. Of course, the FHP is the frictional horsepower, the CMHP is the corrected materials power, which are already given, and E is drive efficiency. So we use 0.88 for typical screw conveyor drive unit with shaft mounted gear reducer motor. So that is the usual drive efficiency to be used. So therefore THP is 0.065 plus 1.5 divided by 0.88. So the resulting is 1.8 horsepower. So the most common standard size of motor is 2 horsepower. So the specification now is the motor horsepower rating is 2 horsepower with the input RPM of 1750. Of course, the voltage more or less is the 440 to 460 volts. So the gear reducer or gearbox horsepower rating is 2 horsepower also with output RPM of 73.64. So based this on the computed actual conveyor speed. So with the ratio of 23.76, that is already computed. For step 4, compute the torque requirements. So based on the data, the bulk density 50 pounds cubic foot per cubic feet, capacity of 47,500 pounds per hour, this length of 16 feet, and of course the degree of incline is 0 degree, and the conveyor diameter, which is 12 inches. So we now compute the torque requirements. So based on the table, some of this data, we will use this on the next computation. Step 4.1, compute the full motor torque. So full motor torque is horsepower times 63,0825 divide S. So the resulting is inch pounds. So the given data of motor horsepower and conveyor speed. So the full motor torque, we get 1,712 inch pounds. So take note, for the proper design of screw conveyor components, the torque rating of the drive shaft, coupling bolts, and the conveyor screw must be able to withstand the full motor torque without failing, and will have an infinite life under normal operating conditions. So it's need to be considered. So for this design, consider the following additional design data. So factor of safety, so I may choose 5. Then the material, carbon steel C1045 for the shaft, pipe, and the bolts. So we can determine the shaft diameter to be used for this screw conveyor. So maximum shaft safe torque required equals factor of safety times full motor torque. So 5 times 1,712 equals 8,560 inch pounds. So step 4.2, determine the shaft size, pipe size, coupling bolt diameter. So maximum shaft safe torque equals 8,560 inch pounds, which is computed from the previous slide, as you can remember. So based on the table, so for the shafting, as we consider, is C1045. So the torque rating, the computed, is 8,560 inch pounds. So based on the characteristic of the C1045 carbon steel, it has a torque rating capacity of 9,500. So we might choose that the shaft diameter that we use, the carbon steel shaft diameter, is 2 inches. And for the coupling bolts also, so grade 5, so we can use the carbon steel type bolt, which is grade 5. So it is still safe because the bolt has the carbon steel bolt grade 5 has the torque rating capacity of 19,000 inch pounds, so it is safe. So for the pipe, we consider schedule 40, so E53 carbon steel, still carbon steel. So in pipe and shear, so still a safe torque because it has a capacity of 14,200, while our maximum torque required is 8,560 only. So pipe in bearing, so bearing stress, so it is still safe 8,900, but our computer is 8,560. So for this design, we might consider that the shaft diameter is 2 inches. So based on the chart So for shaft diameter 2 inches. So the nominal pipe size is 2 and 1/2 inches, and the coupling bolt diameter is 5/8 inches. Grade type is grade 5. So this is carbon steel. So the coupling bolt diameter is 5/8 inch. So that's the end of step 3 and 4 for this design video. So please continue to watch for the step 5 and 6. So thank you for watching. So please like, subscribe, and kindly hit the notification bell for more videos update.